Hi everyone. So I have for you today an international math Olympiad problem from 2002, and actually this problem surprisingly is not hard at all. And all the tools required to solve this problem have been discussed on this channel, and I will connect the theorems to the cards you can see somewhere floating on the screen. Okay. All right. So let's start with the question. Let's draw the problem as we are reading it. Okay. So consider a circle omega with center O. So let's try to draw a circle omega with center O. Okay, so let's call this omega. And let's say the center is O. And let BC be a diameter, meaning if you mark a point B, then I want C to be diametrically opposite. Okay, all right. Let A be a point of circle omega such that angle AOB is between 0 and 120. Okay, all right. So let's draw A to be somewhere here then. Let D be the midpoint of arc AB not containing C. All right, so let's try to roughly draw the midpoint of the arc AB not containing C. I hope you understand. I mean, this is basically the arc of AB containing C, and this is the arc AB not containing C. Okay. All right. Let L be a line passing through O. Okay, some kind of a line passing through O, parallel to AD. All right. So let's first draw AD. First, let's draw AD. Okay. So okay, this is roughly AD, I guess. And okay, so let's draw this like this. Okay, but it's a rough drawing anyway. So let's draw a line L passing through O, and it should be parallel to AD. Okay, so it'll roughly looks parallel. Let L intersect AC at J. So you join A and C, and let's say they intersect at J. Then the perpendicular bisector of OA intersects omega at EF. Okay, so you draw OA and then you sort of cut it in the middle. Let's draw the perpendicular bisector. Something like this. Okay, so when you do this, you will get these 2 points, and this is E and F. Now, what do you have to show? Prove that J is the incenter of triangle CEF. So let's finish the triangle. So C, E, and F. Okay, so if you look at this triangle, the claim is that J is the incenter. Okay, so J should be the incenter. Okay, this problem may look complicated at first, but essentially we'll be able to solve this problem pretty easily if we try to break down what do we know about midpoints of arcs and what do we know about incenter. So let's in fact quickly review all the facts required to solve this problem. Okay, all right, so here are the basic facts. So fact number 1, so both the facts, all these facts are related to the midpoint of the arc. Okay, so point X in each of these drawings is essentially the midpoint of the arc AB. Okay, now the midpoint of the arc AB plays multiple roles. So let's start. The first role it plays is if you have a chord AB, then if you take the center and join it to the midpoint of the arc, then that actually is the perpendicular bisector of AB. Okay, so the first observation is that if you join the center to the midpoint of the arc AB, this is perpendicular. All right, so that's the first fact. Now that's pretty easy to see why actually. Because if X is the midpoint of the arc AB, then that means these arcs are equal in length, but equal arcs contain equal chords. So X is on the perpendicular bisector of AB. O is the center of the circle, and so these are radii. So O is also on the perpendicular bisector of AB. So OX is in fact the perpendicular bisector of AB, because we found 2 points, and perpendicular bisector is a line, and a straight line is determined by 2 points. Okay, so this OX is the perpendicular bisector of AB. All right. So the main point is the center and the midpoint of the arc AB, if you join, that is basically the perpendicular bisector of the chord AB. Okay. On the other hand, if you take the 2 points A and B and take any point C on the arc, okay, on the arc not containing point X, then if you join CX, then CX is the angle bisector of AB. Okay. The second observation is that if you join C and X like this, and this is the angle bisector. Again, very easy fact to prove, because at the end of the day, X is the midpoint of the arc, so these 2 arcs are equal in length. I think throughout we are using the fact that these 2 arcs are equal in length. and equal arcs obtained equal angles. So these two angles are equal. And that's another way of saying that CX is the angle bisector, okay, because these two angles are equal. All right, so the midpoint of the arc plays multiple roles. The line joining the midpoint of the arc to the center bisects the chord AB, and the line joining the point X to the vertex, opposite vertex C, bisects the angle ACB. Now, in fact, let's do a little more with this. Now, let's consider the, ACB, the points ACB. We just now know that, because X is the midpoint of the arc, these two are equal in length. So we further know that, these chords are equal. All right. Now, on the angle bisector CX, mark a point such that these three lengths are all equal. Okay. So in other words, consider the circle with center as X and XA as radius. When you join, it will cut through basically some point on CX. It turns out this point is the incenter of triangle ABC. Okay. So this point is in fact the incenter of triangle ABC. So this fact is part of what is called the Incentre-Excenter Lemma, and we have discussed this on this channel. This is in fact the first video uploaded on this channel. Okay, and this is proved in that video. You will see a card floating above. Now, another theme on this channel was about parallelograms, and that's what we needed in fact 4. So whenever you have two line segments which bisect each other, then you know what, the outer bounding quadrilateral is a parallelogram, and this was discussed on this channel. Further, when these are perpendicular to each other, in other words, they're mutually perpendicular bisectors to each other, then what you have is a rhombus. Okay, all the lengths are in fact equal. All right, so that's another fact, but that's quite easy to prove because, if you join this, these are all 90, we know, and by SAS congruency, all those 4 triangles are congruent, so the opposite sides are all equal. It's a very direct proof. So these are the only 4 facts we need to solve this international math Olympiad problem. Quite basic, right? Okay, so let's move on to this problem. Now I have a more accurate professional GeoGebra picture instead of my hand-drawn picture. So let's try to see what's really happening here. Okay, so we have to show that this particular, we want to show that J is the incenter. Now we know that incenter is the meeting point of the angle bisectors. So basically CA must be an angle bisector, okay, which should mean A would be the midpoint of the arc EF. So if you could prove A is the midpoint of the arc EF, then certainly we will get CA is the angle bisector. So how do we prove A is the midpoint of the arc EF? So let's see, what do we know? We know that EF, right, is a chord, and it has been given in this problem, note, it has been given in the problem that the perpendicular bisector of OA intersects omega at E and F. Okay, so what this means is that EF is basically the perpendicular bisector of OA, right? Which means that this is the perpendicular bisector of OA. You have this and this length equal, and this is perpendicular. Okay, so that's what it means to say EF is the perpendicular bisector of OA. But here's the catch: EF is a chord, and from the center O, you dropped a perpendicular and extended it. Okay, so from fact 1 that we saw a few minutes ago, we know that A must be the midpoint of the arc EF. Okay, A must be the midpoint of the arc EF. So the first conclusion is that A is the midpoint of the arc EF. Okay, further notice that this would mean that OA is the perpendicular bisector of EF. So we have 2 segments which are mutual perpendicular bisectors of each other. So therefore the outer bounding quadrilateral is a rhombus. Okay, so OA equal to OF equal to EA equal to AF. Okay, so the A is obscured, so let me write it here again. All right. Okay, so we have this situation first. But notice OE or OF is the radius of the circle. So further notice OA, not OA, sorry, OE equal to OF is equal to EA. Sorry, so let's write it as OF equal to EA equal to AF are all radii of the circle. Further, we know that OA is also a radius, right? OA is also a radius of the circle. So all this is equal to OA as well. So we have something really awesome. We have now an equilateral triangle. Can you see all these 3 lengths are equal? So what you have is an equilateral triangle. So really what we get now is what we get now is this angle must be 120 degrees. So the angle subtended at the center is 120 degrees, forcing the angle subtended at the arc to be 60 degrees. Okay, so we know that the angle subtended at the arc is half of the angle subtended at the center, so this is 60 degrees. Okay, so we have this as 60 degrees. Further, we already know A is the midpoint of the arc. So the CA is the angle bisector. Okay, already from here we could have concluded, in fact long back, that once you proved A is the midpoint of the arc EF, we could have proved CA is the angle bisector. Alright, so what remains to be proven? Remember, we had to show J is the incenter of triangle CEF. Now remember from the Incentre-Excentre Lemma, the third fact that we showed today, a few slides, one slide ago here, this particular fact. This particular fact tells us that to locate the incenter is to say that these lengths are actually equal. Okay, so let's use that to our advantage now. Okay, so all we have to show is, let me change the color so that you can very clearly and visibly see it. So you have to show this JA length, which is on the angle bisector. Remember, we already proved CA is the angle bisector. So we have to show this is equal to EA. Okay, in fact, let's color code it so that all congruent segments have the same color. So we have to show basically this JA is also the radius. So we are done if we could show AJ is radius of the circle. Okay, is congruent to the radius of the circle. Okay, so how do we show that? So that's the last step to be shown, and if we do that, the proof is over. Just from Incentre Excenter Lemma, we know point J lies on the angle bisector CA, and further JA is equal to AE, and then we are done. But AE is the radius, so we somehow have to show JA is the radius. So let's look at a new drawing because it's quite convoluted at this point. So we have to show JA is the radius. Okay, we have not yet used the fact that these lines are parallel. Okay, so AD and this line are parallel, it's given in the problem, and we have to show JA is the radius. This is a very natural thing to complete here. Notice that OD is also a radius. So if you could complete this, looks like a parallelogram if you have drawn it accurately. So what we will do is we will try to join OJ and DA, which is already parallel, and we will try to look at this line OD, this radius OD, and we'll try to prove that OD is parallel to JA. Notice if we prove OD is parallel to JA, we are done, because already OJ is parallel to AD, it's given in the problem, and if you prove OD is parallel to AJ, then opposite sides are parallel, which means it's a parallelogram, something we have again covered in this channel, right? So we just have to show we have to just show it's a parallelogram, right? So that will force OD to equal JA, which is what we have to show. All right, so that in other words JA is the radius. All right, to show it's a parallelogram, we have to just chase some angles. So let's chase the angle. So we have to somehow show that these are parallel to each other. Suffices to show OD is parallel to AJ. All right, now how do we show OD is parallel to AJ? We have to maybe show this angle is equal to this angle. Okay, I don't see other ways of doing this, or maybe we could show this angle is equal to this angle. Maybe it's better to show this angle is equal to this angle, because this is the angle subtended at the center, and that would relate to angle subtended at the arc, and we can do something with it. So let's see it. So let's actually draw DC. Okay, let's say this angle we have to prove is equal to the other angle, so let's call this angle 2x. Okay, if that angle is 2x, then this angle is x. Angle subtended at the arc is x if the angle subtended by the chord AD at the center is 2x. So we have to somehow show this is 2x. Okay, we have to show somehow this is 2x. How do we show this is 2x? All right, we have not yet used B is diametrically opposite to C. Maybe that's useful. Let's see what to do with that. So let's join B and C. Okay, let's join B and C. What do we get? Okay, so you have OC is the radius. OC is the radius. OA is also a radius. That is true. It's been given that D is the midpoint of the arc AB in the problem. D is the midpoint of the arc AB. So if this line here, if this angle is x, then that would mean this angle is also x, right? So because D is the midpoint of the arc AB, these two arcs are equal, so they'll subtend equal angles. So this particular angle is also x. This angle is also x. So now we know this angle is 2x, but this is an isosceles triangle. OAC is an isosceles triangle. So let me write down all the steps now. So if we first show proof, so let's write down the proof. So almost done. So let's write down the proof. The proof is first join. Notice that OB, let's in fact write it as BCD angle is equal to DCA, because arcs BD and AD are equal. Both are equal to x. So therefore angle OCA is equal to 2x. But in triangle OCA, OC equal to OA because they're both radii. Therefore, in isosceles triangle, base angles are equal. So angle OAC is equal to the other base angle OCA, which we already know is 2x. So we know OAC is 2x. Okay. Notice that we already know AOD is also 2x. In fact, that is because it is twice the angle subtended at the arc DAC. Okay, maybe I should write that step down. Okay, so that's clear to everyone. This is 2 times angle DCA, sorry, which is 2x. Okay, so therefore we are done. We have shown that AOD and OAC are both 2x. So AOD and OAC are both 2x. Okay, so which means that these two lines are parallel. It's been given these two are parallel, so in fact it's a parallelogram. So JA is equal to OD, but OD is the radius of the circle, so JA is the radius. Okay, so indeed, therefore J is the incenter of triangle CEF. Awesome, right? Bye.